It's the intro to modern, beginning of the end. Where will it start? I don't know, but it starts right here, right now. Thanks, Gio, for sharpening that pencil right now. This is what happens whenever a school district thinks it's a great idea to offer virtual classes while the in-person classes are going on. It's a mess. For anybody out there seeing this in the distant future, don't ever do this. Hire other people to run online courses. Anyways, rant over, let's begin. Okay, so modern physics isn't really that modern. It's a lot of late 1800, early 1900 stuff. But one of the first things that we do need to kind of talk about before modern physics actually goes back into E&M. E&M was like modern before the modern era existed. And if we went back into E&M, one of the equations we might have remembered was that a force acting on a moving charged particle was equal to Q V cross B, where this cross product here led us to do a lot of this stuff with right-hand rules. And if this doesn't mean anything to you, go back and watch all those old videos on the right-hand rule, okay? And we also saw that in perfect scenarios, or just scenarios in general, we could think of this as a centripetal force, which was mv squared over r. This is like if you were acting through a constant B field for this particle, and you had a large enough B field, you could like just go in a loop, okay? Well, one of the questions that is initially asked is, how do you get the mass of something like an electron? Or how do you get the charge of something like a single electron? That's a really weird thing. Like, I don't have a scale small enough to get the mass of an electron, because the mass of an electron is super tiny. It's like 9.11 times 10 to the negative 31st kilograms. That's super small. I don't have a scale to measure that. Furthermore, like, how do I even get just one electron, like, by itself? Very, very good tweezers? Like, that doesn't make any sense. Some of the most early experiments to try to figure this out weren't actually figuring out mass or charge. They were figuring out a mass-charge ratio. Because what we could see here, through some clever manipulation, is we could say that Q over M was equal to V over BR. And this would give us a ratio of these terms here, which was useful, but it wasn't either of them completely. But if we could get one of them, either the charge or the mass, then we could start working and finding other things. Through a series of experiments, Robert Milliken did what we now know as Milliken's oil drop experiment. This experiment is a pain in the butt. Like, it's a super pain. Because what Milliken actually did is he set up a chamber. And in this chamber, he would have like a little spritzer or an aerator bottle that he would spray in, kind of like a perfume, in oil. So there would be a bunch of oil drops floating around here. But they weren't floating. They would naturally, due to gravity, fall. So what did Milliken do? Well, it turns out when you aerate these oil drops into this space, the oil drops become electrically charged. So what Milliken did is he put a positive and a negative plate, and he could tune this plate, he could tune this electric field that is generated to push up on these drops. Through a series of clever calculations and understanding how objects move in free fall for a sphere, which starts getting extremely complicated, but if you're interested in that, go find the papers online. Milliken was able to determine, generally speaking, masses of the particles. And what he was able to determine by switching this electric field was he was able to determine that the charges he was getting off of these oil drops, which, remember, an oil drop is not one electron. It's multiple electrons. It's multiple things, right? And they're all different sizes. But he started to find that on plotting these oil drops, he got this very nice straight line. And it turned out that the equation he found was that charge was equal to some integer number of our elementary charge, which was that integer number of the 1.6 times 10 to the negative 27 coulombs. This is what he was able to determine through graphical measures. So every single particle he found had an integer number of electrons, or fundamentally charged particles, which was an amazing thing at this point in time. Super finicky to do, though, because you've got to look through like an eyepiece in order to see the particles, and if for a second you blink and those particles move, or you lose track of whatever it is you're looking at, the data's gone. Because of this, there are actually some people in the science community that look at Milliken's work and the data he collected, and they accuse him of like cherry picking values. He kind of had this idea in his mind already of what he wanted out of it, and he kind of cherry picked values to get that. But at the same time, he also has this insane experiment to even try to do. So, potato there. Either way, this idea of the oil drop experiment really got us into start thinking about, hey, this is a fundamental particle here of an electron, and it is like a small amount of charge. So this right here, we start getting into the idea of modern physics and start looking at smaller particles and what's going on. What we're going to take a look at in our next video is we're going to take a look at the work of Max Planck and his quantum hypothesis and where that takes us, kind of combining the world of astronomy, mathematics, and some lucky guesses. But until then, this is finished. Adios, and take it easy.